When we study the remnants of antiquity, we often struggle to see the past on its own terms. Instead, we scan the ruins for reflections of our own modern machinery, projecting our current technological state onto ancient stone. This Abydos carving is a palimpsest. Seti I carved the original, but Ramesses II plastered over it to recarve his titles. As plaster degraded, both layers revealed overlapping shapes. Our brains interpret this accidental superimposition as a helicopter and other modern vehicles. No physical machinery exists in the record to support a literal interpretation of these shapes. The ancient blueprint theory falls apart when we realize the helicopter only exists because of the specific way these two sets of hieroglyphs overlap. Obsessing over non-existent aircraft is a distraction. It blinds us to the verifiable, breathtaking engineering ancient civilizations actually utilized, technologies that operated on principles we are only beginning to reevaluate. Instead of looking for shadows of our own machines, we must look at high-precision measurement systems verified by the physical record. The Antikythera mechanism, for example, used a system of differential gearing to calculate lunar cycles and eclipses. It is a documented analog computer capable of tracking celestial mechanics with mathematical precision. Artifacts like the Baghdad battery suggest electrochemical capabilities, while Roman dodecahedrons point towards sophisticated geometric surveying tools. In 1322 CE, Chinese engineers built a mechanical seismoscope. It used an internal pendulum to detect and indicate the direction of distant seismic phase shifts. Modern engineering relies on artificial, closed-system sensors. Ancient engineers utilized a different philosophy. They turned universal constants, gravity, light, and the behavior of water, into their primary measurement tools. The Merkhet leveraged localized gravity via a plumb line and a sighting tool. This allowed astronomers to achieve arc-minute precision when tracking the movement of stars across the meridian. The Neolometery utilized stone scales to track flood variances. By monitoring the fluid dynamics of the river against these carved markers, they could predict the agricultural output for the entire Nile Valley. These were certainly not primitive tools. Ancient engineers turned the physical environment itself into a civilization-proof, high-precision laboratory. This universal sensor philosophy extends beyond tools and into the very way they stored data, utilizing written steganography and megalithic architecture as durable information systems. This leads into the friction surrounding sacred geometry. Modern science often rejects the field because many interpretations fail to go beyond basic pattern recognition. To move past speculation, we have to respect the epistemological boundary. A pattern can serve as inspiration, but it requires mechanical validation and a testable framework to be treated as an engineered reality. The Rind mathematical papyrus provides this empirical proof, documenting their explicit comprehension of advanced geometry. It demonstrates a mastery of unit fraction decomposition and universal constants. The calculations confirm they utilized proportions like phi and pi as functional engineering standards. This foundational mathematical literacy wasn't just for papyrus, it was applied to their megalithic structures, turning buildings into physical data storage. The Great Pyramid of Giza functions as a macro-scale encoding of the golden ratio and the dimensions of the Earth. Its sheer scale serves to preserve these mathematical relationships indefinitely. Likewise, the Dendera zodiac is a calculation tool in stone, tracking the star positions and the precession of the equinoxes over vast cycles of time. These civilizations used geometric ratios not as mere art, but as a culturally redundant medium for storing data that would remain translatable across different languages and eras. While Egyptian architecture utilized rigid stone, the Sumerians worked in wet clay, a high-viscosity fluid substrate that captures the physics of the person making the mark. Because wet clay is a dense fluid, any stylus pressed into it encounters immediate, heavy physical resistance. This allows the medium to act as a 3D record of vacuum viscosity, capturing how the material pushes back. We usually read these tablets as linguistic records. However, the varying depths and angles of these marks suggest they function as a 3D metric tensor, mapping physical forces into a handheld format. The individual cuneiform wedge is a tetrahedral volume. When pressed into the clay, it functions as a vortex operator, creating a geometric sink in the fluid medium, that displaces the material along specific lines. This physical interaction maps the dynamic push of the fluid medium. The depth of the wedge and the resistance of the clay provide a direct measurement of the pressure vectors involved in the mark. The specific horizontal, vertical, and diagonal angles of these wedges act as phase-shifting offsets. By altering the angle, the scribe was calculating how wave phases shift as they interact with the geometry. Overlapping wedges plot contextual noise resonance. This calculates exactly where multiple sources of vibration touch and amplify, creating a map of the resulting interference patterns. Modern scholars often treat these tablets as simple inventory lists. Structurally, however, they are three-dimensional arrays designed to track the topological pressure of a fluid universe. The Sumerians were cutting with the organic grain of reality, using clay to hard-code the complex physics of resonance and pressure into a durable, handheld medium. This concept of physical resonance mapping scales from handheld clay up to the megalithic architectural arrays of the ancient world. Large-scale stone arrays respond to environmental vibrations. By tracking how these massive, rhythmic columns resonate, ancient builders could monitor structural shifts and subterranean activity, like seismic phase shifts or Nile flood surges. The physical architecture dictates how standing waves behave, amplifying, canceling, or shifting phase as they bounce between these confinement points. This acoustic mapping appears in Egyptian hieroglyphs, where line art depicting waves interacting with pillars matches the expected resonance spikes of a physical array. These structures functioned as massive, environmentally integrated sensor grids, allowing the civilization to monitor the resonance of the natural world through the architecture itself. To properly decode these sites, we must analyze the structures through the lens of wave mechanics, looking past the art to the physics of the stone. To bridge the gap between pattern inspiration and mechanical proof, we need modern systems engineering to test these ancient frameworks. One methodology involves running 3D vector steganography algorithms over high-resolution topographical scans of these artifacts to analyze their precise geometric depth and angles. This allows us to measure the actual physical resonance spikes and harmonic ratios hard-coded into the carvings, moving from observation to objective data. The result of this robust, redundant form of information storage is remarkable durability. By embedding data in the geometry of the physical world, they ensured the information would survive the natural cycles of collapse. Ancient civilizations encoded the eternal realities of fluid dynamics and resonance into the indestructible geometry of nature. They utilized the baseline parameters of the universe to ensure their knowledge would persist long after their empires turned to dust.